All right, now that we've defined electric charge, we need to talk about how they work together. So that's something which is called the electric force and Coulomb's law. In 1785, Charles Coulomb established how charge-force objects act on each other. If two objects bearing charge Q1 and Q2 are located at a distance r apart, they each exert a force F on the other, according to this law, that the force is some constant times the magnitude of Q1 times the magnitude of Q2 over the distance between them. So we have charge Q1, charge Q2, and we're defining the distance between their centers as r. Why the absolute value bars? Because charge can be both positive and negative, and we're looking for the magnitude of the force, so we want to force everything to be strictly positive. You can get cute and try and define it in a vectorially satisfactory way. It turns out to not be worth that kind of effort. It's better to think that the size of the forces are dependent on the size of the charges. As for the direction, the force should tend to move like charges apart, but bring unlike charges together. Like charges repel, opposite charges attract, and so the force points in such a way as to do that. Two negative charges repel each other, two positive charges repel each other, but a positive and negative pull together. And there's a missing fourth case, which would just be the positive down here and the negative up here doing the same sort of thing. Once we've defined the unit of charge, which, as we know, we not coincidentally call the Coulomb, we can figure out the constant. Coulomb himself used a torsion balance similar to what Cavendish had used to measure capital G from the Newtonian law of universal gravitation. If they remember, that was sort of this idea of having some sphere of thing here and some sphere of thing here connected by a light rod and a thin wire, and then bringing something else nearby so as to torsion this way but repel it this way. And he arrived at that the constant in his law, his force law, would be 8.99 times 10 to the 9 newtons meter squared per coulomb squared. And those are bizarre units, just like in the law of universal gravitation, where G has bizarre units of newton meter square per kilogram square. And the reason in both cases is just to make the equation balanced, to make sure that it yields out the force law. It's what converts our unit of charge into a unit of force. You should note that K is large-ish. It's not crazy large, but that means small charges can produce significant forces. This is the opposite of the gravitational case, where the gravitational constant was so tiny that you need astronomical gravities to produce human-scale forces. Here, K is large enough that you can use relatively small charges to produce human-scale forces. And then it gets a little weird. It turns out, however, the form that we have for Coulomb's law gives rise to lots of awkward and weird formulas later, whereas that constant K shows up in bizarre and strange ways. After much grief, the physics community realized that things would be easier if instead we had written Coulomb's law as the force is 1 over this weird thing, 4 pi epsilon naught, times the product of charges over the distance squared. In other words, we have replaced K, a nice simple number, with this really strange thing. That we write that K is going to be 1 over 4 pi epsilon naught. Epsilon naught is called the permittivity of free space. It tells us how easily electric forces cross vacuum. Later on, we'll talk about it. Really talks about how the electric field threads throughout space. It's a fundamental law, constant of the universe, and shows up in lots of other places. We can see from just solving over this formula that epsilon naught has the weird values of 8.85 times 10 to the minus 12 coulombs squared per newton meter squared, which is, again, a weird unit designed just to make all the units work out. Right? Nothing spectacular there. We'll see later there are actually more convenient units to put into this, but right now they wouldn't make any sense, so we're going to leave them out. Surprisingly, it turns out that Coulomb's law itself is not used that much in electrostatics and really not at all in electric dynamics. But epsilon naught keeps coming back, and so there are a lot of formulas that are made significantly easier and much simpler if we use this form for Coulomb's law, specifically something called Gauss's law, but really some other things that flow from that. And later on, way later on in electrodynamics, we turn out that in fact things like the speed of light is related to the square root of epsilon naught. So if we had that K, that'd also be these weird square root 2 pi's and stuff. So we just do this at this stage, even though it is legitimately a little learner hostile. We introduce this weird structure now to make life much easier for you later. Notice that Coulomb's law looks a lot like Newton's law of gravitation. We can often use results from the earlier to see our way to solutions to the latter. But keep in mind that gravity is only attractive. There are no opposite sign masses. There are no negative masses. And this does complicate things. The similar forms mean that we can just use the Newtonian shell theorems. Specifically, the electric force due to a spherically symmetric distribution of charge when outside of that distribution is the same as due to a point charge of the same magnitude located at the center. That's a lot of verbiage. What we're saying is if we have some collection of charge, let's say that's plus Q, and we are out here asking what is the force on some other charge, little q, because they're located a distance r from the center of that sphere, that this is the same as having little charge q and big charge plus q at the center separated by the same distance. Outside the spherical distribution of charge, we can't tell that we're outside a spherical distribution of charge. It looks like it's at the center. It also leads to the kind of weird thing like, hey, what if we're inside? So we have some amount of charge which is spherical, but I want to know what's happening if I have a force, some distance like this. And then what I do is figure out how much charge there is within that space. So only this little charge would count. And the stuff outside does not exert a force, just like we have with gravity. And again, even though we don't use Coulomb's laws a lot, this is a useful thing to keep in mind, even as we do later things, that because it works with Coulomb's laws, anything that follows from Coulomb's laws, it will work as well. And we'll use that from time to time. It'll be particularly important when we talk about conductors. All right, the charge of sphere 2 is twice that of sphere 1, which vector below shows the force of 1 on 2 if we were to suddenly reduce the distance to 1/2 of r. Conveniently, the original force is here, and we can see that since the force is proportional to 1 over r squared, and this has become 1 over 1/2 r quantity squared, which is actually 4 times 1 over r squared. It should be 4 times as long, and none of these existing guys are 4 times as long. This is only barely twice. So therefore we see that, almost a trick question, it's none of these. Which is the direction of the net force on the charge at the lower left? So we want, what is the net force on this charge? Well, walking through it, if we give each of these their own color, so blue and green and purple. Well, the purple charge repels the other charge this way. Hey, just like that one. And this blue charge repels the one this way. When we add them up, that means that together they have a repulsion which is along direction B. Something like that. But when we go back here and we say, what about the green one? Well, the green one is also pushing in direction B. So the overall would have to be direction B, which I've obscured, but direction B. Because all of them push in that direction, and the off-axis of those cancel out for the other two. What is the direction of the net force on the charge at top? This one. Well, the blue is going to repel it something like this, and the purple is going to attract it something like this. So we can see that together they're going to be along that direction. All right, and here we have the charge of the direction on the minus q charge is which of these? We see, of course, that the well, I'm going to give them different colors. So this versus that. The blue one is going to repel a little bit, right? It's going to force the charge to the right. But the red one's, of course, going to call it back. And the question is who wins. So if we take this as the repulsion, what we know is that the attraction term is somewhat closer, so it would be somewhat smaller, and therefore the net force would point to the right.